There's one function in all of mathematics that has a truly magical property. Its derivative equals itself. Its integral gives back the same shape. Up to a constant, no other function does this. Today, I'll show you why this is true. Not just state it, but prove it from multiple perspectives. First, let's meet the number e. It's called Euler's number after the mathematician Leonhard Euler. E equals approximately 2.71828. Like pi, it's irrational and goes on forever. The classic definition of E comes from compound interest. Imagine investing $1 at 100% interest. As we compound more frequently, the value approaches exactly E. After 1 year, you'd have E dollars about 2.72. But here's the geometric reason why E is special. Let's look at different exponential functions. All exponential functions pass through the point 0, 1. But their slopes there are different. For 2 to the x, the slope at x equals 0 is about 0.69. For 3 to the x, it's about 1.10. But for e to the x, the slope at x equals 0 is exactly 1. That's what makes e special. E is defined as the unique base where the slope at x equals 0 is exactly 1. This is the geometric definition of e. Now let's prove that the derivative of e to the x equals e to the x using the limit definition. The derivative is defined as a limit. Applying this to e to the x, we get e to the x plus h minus e to the x divided by h. Using the exponent rule, e to the x plus h equals e to the x times e to the h. Factor out e to the x. Since e to the x doesn't depend on h, we can pull it outside the limit. Everything hinges on this limit. Let's use the power series to prove it rigorously. Subtract 1 and divide by h. Watch what happens. Simplify, we get 1 plus h over 2 factorial plus h squared over 3 factorial, and so on. As h approaches 0, all those terms with h vanish. We're left with exactly 1. Therefore, the derivative of e to the x equals e to the x times 1, which is just e to the x. Proven. Let's see what this means visually. At every point on e to the x, the height of the curve equals the slope. At x equals 0, the height is 1, and the slope of the tangent line is also 1. At x equals 1, both the height and slope are e, about 2.72. At x equals 1.5, again the height 4.48 matches the slope exactly. This is the magic of e to the x. The curve is its own slope everywhere. Here's another beautiful way to see why this works, the power series perspective. E to the x can be written as an infinite sum, called the Taylor series. Now watch what happens when we differentiate term by term. The derivative of 1 is 0. The derivative of x is 1. The derivative of x squared over 2 factorial is x. The series shifts left and becomes itself again. This is why the derivative equals the original function. This is why e is called the natural base. For any other base a, the derivative carries a scaling penalty. For example, the derivative of 10 to the x is 2.3 times 10 to the x. The rate of change doesn't match the value. But for e, the natural log of e is exactly 1, so there's no scaling penalty at all. This is the natural property. Only with base e is the rate of change perfectly synchronized with the value. Now let's derive the integral of e to the x. We'll use the power series again. Remember the Taylor series for e to the x. Now let's integrate term by term. The integral of 1 is x. The integral of x is x squared over 2. The integral of x squared over 2 factorial is x cubed over 3 factorial. Notice the pattern. Each term integrates to the next term in the series. The series shifts right. So when we add them all up, we get a constant c plus x squared over 2 plus x cubed over 3 factorial, and so on. Notice this is e to the x, but missing the leading 1. So we have c plus e to the x minus 1. But since c is an arbitrary constant, we can absorb the minus 1 into it. C minus 1 is just another constant. Therefore, the integral of e to the x equals e to the x plus c, rigorously derived. Bonus. We can use our result to derive the derivative of the natural log. Let y equal natural log of x, then e to the y equals x. Differentiate both sides with respect to x. Using the chain rule, we get e to the y times dy dx equals 1. Solve for dy dx. Since e to the y equals x, this becomes 1 over x for positive x. And here's the beautiful symmetry. E to the x is both its own derivative and its own integral. Up to a constant multiple, e to the x is the unique function with this property. And that's the complete story of e to the x, the most magical function in mathematics. To master the math behind calculus, check out the Pantheon. link in the description.